Right, so this week is Kirchhoff's rules. Um, it's also paired. We have a quiz this week, quiz two. Uh, Take it on your own time. You have 20 minutes to complete it, just like last week, or just like the last one. It's going to be a bit more difficult since we are gradually going over more difficult concepts in lab. The quizzes are going to get a bit more difficult, so try to make sure you're ready. Make sure you've reviewed um, what we've done on the previous labs. Okay, and I made it less questions since it is a bit more difficult. Okay, let's go to the lab. Let me share my screen. So you see here Kirchhoff's rules. Going in, this one is, this lab is going to be a bit more difficult than the last. So you can think of last week's lab as like the warm up to this one. We go in here to the instructions. It's quite literally going to be creating a circuit in that program we used last week, and just there's going to be a bit more calculation and a lot more complex arrangements. So let me, show you a few in the and right, the pre-lab has gone over quite a bit of this, and also you can still always rewatch that one too. In a bit, I'm going to talk a bit about the two rules, the voltage and current rule. And here's some theory that might help you. And going into the simulation. In the simulation, we're going to now select lab and make this circuit that's sort of presented right here. So same thing, let me go to, it says, so now we're going to go to lab. And we're given a few different tools over here on the right. And I believe everything is the same on the left. Yeah, we're only going to use what's told for us to use. In any case, we're just following step by step like we always do. For this one, it's rather simple. Progressing, uh, again, sort of introducing how to measure voltage if we've forgotten from last week. Voltage and current is going to be one with current. And then we're going to make the circuits a bit more complex. We're going to, this one's adding light bulbs. You can think of light bulbs kind of like resistors. Not necessarily in that there is a bit more going on, but again, just measuring sort of where it says to measure, kind of like last week. Okay, a bit more complex. And I believe I saw some very uh, complex ones at the end, but there's this table for you to fill out, sort of related to that other one with A, B, C, D. Okay, since it's a lot of measurements, this will keep it nice and clean. Here's one of the most difficult ones of, this would be difficult if you just had to calculate. I think we're just measuring this one. Yeah. Okay. Otherwise, and at the very end, we're going to be doing some unknown resistors, and it'll sort of tell you how to get there. So ultimately, let's go back. ultimately, think of last week as the warm up. This week is more sort of driving in the point of Kirchhoff's rules. Okay. And it's always sort of step by step. Remember, we're going to have our introduction at the top, and I don't think, let me look down at the bottom, screenshots, and right, so at the end, you are going to have to put your own conclusion, sort of a paragraph wrapping up what we did in the lab. Okay, I think that is it. Are there any questions about the procedure? Sort of the big brother of last week's lab. And I have the video for that one up still also. Okay, since it is a bit more, it's the same thing but more difficult. I don't have any kind of like thing that I'm specifically checking today. I'll just let everyone go. I'd suggest that you stay and work on it, since you can see it does ramp up the difficulty a bit. But after my notes, I'll say the people who want to work on it could stay. If you feel you can do it on your own later, that's up to you. All right, let's go over some notes. They're also going to be like last week's notes, because I sort of touched on it a bit. Let me okay. Okay, we need to do that. All right. Now we are doing rules. Kirchhoff's rules. Very simply, there are two Kirchhoff rules that we're going to go over. I just sort of suggested you look them up. Might have helped with last week's lab. But the two that we're concerned about are the voltage rule and it's also called, you could maybe just say loop rule. Loop rule. It's also kind known in some places. And there is the current rule, also known in some places as just the junction rule. Okay, I'm not sure. I don't believe they are numbered, so you might see one numbered before the other. They're more or less just referred by their name. The voltage rule, the definition is the sum of the voltage in any closed loop is 0. So let me phrase that in my own way. Or I could just say make sure that you know that it is any closed loop. equals 0. Okay, I will just sort of state these at the beginning, and I'll show you a bit more with the little picture below. The junction rule is, I can break it down to saying that the current flowing into a junction is the same as the current flowing out of the junction. So let me just put that. Current I'll say enters a junction. Is the same as the current that exits the junction. All right, so enters the junction, same as the current that exits the junction. Okay. So what do these look like? I could state these, but what do they mean? Very simply, let me do the loop rule, the voltage rule. If we had that battery, sort of that arrangement we've seen last week in my notes, we had a battery. Again, large was positive. And in one example from last week, I had 2 resistors, and that made one big loop. Okay, we saw from last week that whatever amount the battery was putting out, how much voltage it was supplying. So for the lab, it was 9 volts. Within that closed loop, you see this loop is closed. The sum of the voltages was a 0. So since there were 2 resistors last week, R1 and R2, if the resistances of these two were the same, using Ohm's law, we can find the current, but ultimately, since the resistances were the same, they were both taking the same amount of voltage each, meaning that the sum was 0. And we saw it for that first one. That was taking 4.5. That was also taking 4.5. When the resistances changed, say, R2 was larger, we noticed that the amount taken from each resistor was different. We saw that the first one was 3 volts, and that larger resistor then took 9 volts, 6 volts. The sum was still 9 of these two, this and this. So we saw that with the series and also with the parallel example. Okay, 9 volts, positive. This is where I was suggesting for how to look at this, you first I see. So someone asked, do we disregard negative values or just assume they are positive? So what you can do is either, this is where you're assigning a direction to the circuit. So what I would do is, if I want to start out by calling this a positive 9 volts, I say the current is going this way. That's just the way I'm making the current flow for my calculations. I'm going to say that these R1 and R2, they are taking the negative voltage, therefore making them the sum actually be 0. So that's positive 9 from the battery, and then minus 4.5 from R1, and minus another 4.5 from R2. This, I want to say it's up to you. You can also, if it, doesn't make sense to make these negative for you, you could say that the battery starts with negative 9 volts, and then it's flowing that way. It's really just a matter of how you want to think of it. I like to say like the battery is supplying the voltage, so it's providing, so positive, and the uh, light bulbs or resistors, they are consuming, so it's negative. And so in my mind, that's how I make sense of the negative voltage for these two. For this parallel example, 9 volts supplied by the battery. And what we saw was that each resistor, the voltage across each resistor was also 9 volts. 9 volts and 9 volts. It's much different than the, 4.5 and 4.5 of this one. Series and parallel. Okay. What's happening? Why is R1 now taking only not taking 9 volts? Well, you have to remember the circuit is only concerned with whatever is a complete closed loop. So look at this small little, let me make it another color. Make it red. So we have this small loop here. This here. That is a small loop, and we'll call that loop 1. And within loop 1, there's one battery and one resistor. So one battery, one resistor. For we may not have noticed at the time or known at the time, but this is Kirchhoff's voltage rule or loop rule in play. So this is a closed loop. Within any closed loop, the sum of the voltage is 0. So again, I could say a positive 9 from the battery, and I could say that first resistor is taking a negative 9 volts. That's 0. That's how it sums to 0. And we had, for that other resistor out here, you can think of it in two ways. you could think there's this larger loop that goes on the outside. There's this large loop that flows around the outside. This large loop I will call loop 2. And within loop 2, there is one battery. It goes out and around, and there's only one resistor in loop 2. So in loop 2, I should have done this top one in red, but so within loop 2, there's a battery, and there's this resistor taking that 9 volts. Okay, so we have a way of sort of seeing how there can be many different loops, but you might also be thinking to yourself, what about, I can kind of see another loop happening here. Let's do this. Let's say I wasn't, I couldn't find this outer loop for some reason. I couldn't find loop 2 for some reason. But I did know the voltage taken from this resistor. I can make a third loop. And I could go in here on this side. But you might be thinking, there's no battery. How can there be a flow of electricity? How can there be a loop? Well, there is a loop. Consider this loop 3. And in loop 3, this is where I will have to, decide positive and negative, which one I want to call positive, which one I want to call negative. So if I already know that resistor 1 has 9 volts across it, I can then say there's 9 volts, there's one resistor in loop 3. No, there's not, there's 2 resistors in loop 3. One of them is 9 volts, and we're going to call that a positive 9 volts. What is that other one? And we have to remember Kirchhoff's voltage rule that the sum has to be 0. So this is another way using loop 3 to figure out that this resistor on this right hand side also has to be 9 volts. And we would just call it negative 9 volts. All right. Hopefully that doesn't confuse too much. But make sure to always see where the loops are for the voltages. And this is basically Kirchhoff's voltage rule. If you see it written somewhere fancy in a math term, it is like this. It is this summation sign. The sum of all voltages is equal to 0. So that just means if you add up all of the voltages, similar to how I did down here, equals 0, 0, 0. Okay, next. The current rule, current. the current in is equal to the current out. That's how you can summarize that. Let me just do a blank sort of junction somewhere out in space. I don't want to do a full circuit. Let's just say there's this wire coming in and it hits a junction. Junctions are usually just dots on a circuit diagram. And it's going to be split into two paths. Let's say the current is flowing this way. And let's say that after this junction, we are going to say that the current is flowing that way and that way. So let me just make arrows like that and like that. And we can measure the current in these three positions. I1, call it I2, we'll call this I3. And you have to make what you would do is determine what you notice as the current coming in and set that equal to the current going out. So this one I see this is the current going in. So I1 is equal to the current going out. I2 plus I3. This is also what we saw last week. And it's true for any junction. So if we had, I forget what the values were for this in the lab, but if this is, say, 5 amps coming into the junction and we're given a problem and we know something over here on this side of the circuit has a current of let's say like 4.5 amps, then we know that at this junction that remaining bit of current, I2, has to be that leftover bit. So this had to be 0.5 amps. So this is, currents sort of splitting in two directions. It's the same for current meeting at a junction somewhere and combining. This was also seen in last week's lab. I'm going to keep the lettering the same, but we're going to have to change the formula. So what's coming into the junction, I1 and I2, what's going out, I3. And I could just put in values here. Coming into the junction, 1 amp. And from this direction, there's, 2.5 amps coming into the junction. We expect that this third current over here should be 3.5 amps. And we don't even have to measure it, since we know that will follow Kirchhoff's current rule or junction rule.
Wait, so the bottom's supposed to say I3 equals I1 plus I3, or?
Oh, I made a mistake. 2. Right, so that going in and in, that's coming out. 1 plus 2 equals 3. There we go. All right. Are there any questions on these rules? The whole lab sort of revolves around these. And I think there's a lot more measurements than we have to calculate, so I don't think it will be too bad, but it is good to know the rules in case you did have to calculate something. Okay. Let's see. All right, I'm going to clean these notes up a bit and put them up later along with the video. Um, yeah, I think this is, maybe I can make this a bit cleaner. All right. I'm going to open up breakout rooms, but I'm not checking anything off today. Let me make them 8. I'm not checking anything off today. It is a bit more involved than last week. So however long you want to stay and work on it is up to you. Yeah.